All right, so are you ready to dive into the future of nuclear power with me?
Sounds like a plan.
Because with this deep dive, you guys sent in some really, really interesting research on how we can have nuclear energy without those iconic giant cooling towers.
Yeah.
Or the fear of meltdowns. Honestly, it sounded too good to be true at first.
You know, it really does sound like something out of a sci-fi movie, right? But
yeah.
What's exciting is that we're talking about real, tangible advancements in nuclear technology, specifically with small modular reactors, or SMRs. For short.
SMRs, right? I've heard about these.
Yeah.
They're designed to be like compact and super safe and way more efficient than traditional nuclear plants. But what really blew my mind was the tech they're using to actually generate the electricity.
Yeah, that's right. We're talking about ditching those massive, clunky turbines.
Yeah. And
replacing them with these two incredibly innovative systems called heat to light to electricity conversion, or HLEC.
Okay.
And thermophotovoltaic conversion, known as TPV, both aim to make nuclear energy cleaner, safer, and more efficient than ever before.
Okay, so let's unpack this, starting with HLEC.
Sure.
So you have the reactor core generating a ton of heat, right?
Right.
But instead of using that heat to create steam and spin turbines, HLEC converts that heat directly into light.
Exactly. And then that light is captured by specialized photovoltaic cells.
Oh, cool.
Similar to what you see on solar panels.
Okay.
To generate electricity, it's a remarkably elegant solution that eliminates a lot of the complexity and potential points of failure associated with traditional nuclear plants.
So no more giant spinning turbines.
That's right.
That's a game changer in terms of size and safety, right?
Absolutely.
Yeah.
HLEC systems are potentially much smaller and more compact, which opens up a whole world's possibilities for where we can deploy nuclear power.
Yeah.
Think about it. Small modular reactors, they can be easily transported and installed in remote locations, providing clean energy to communities that need it most.
That's incredible, but I'm curious about the specifics. What kind of light are we talking about here?
Oh, yeah.
Is it like a giant glowing orb or something?
Not quite. These reactors operate at extremely high temperatures, around 800 degrees Celsius.
Wow.
At that heat, they emit light primarily in the near-infrared range, which is invisible to the naked eye.
Ah, so it's more like a hidden superpower then.
Exactly. And here's where the science gets really cool. There's a material called gallium antimonide, or gasblé for short, that is remarkably efficient at converting that near-infrared light into electricity.
Wait, so we have this invisible light source and then this special material that can basically capture that energy and turn it into electricity. That's amazing. It's like a perfect match.
It really is. It's a testament to how advancements in material science are driving these groundbreaking innovations in energy technology. But of course, there are still challenges to overcome.
Like what, is it hard to find this gallium antimonide stuff?
That's one of the hurdles, yes. Gasblé is a relatively rare and expensive material, so researchers are constantly looking for ways to improve its efficiency and reduce its cost. Another challenge is something called spectral optimization.
Spectral optimization. Okay, that sounds complicated. Can you break that down for me?
Sure. Think of it like tuning a radio. You need to make sure the emitter, the part that's generating the light, is producing the right kind of light. The specific wavelengths that the cells are best at absorbing, if the wavelengths are off, you lose efficiency.
So it's all about fine-tuning that energy transfer for maximum power.
Exactly. And scientists are exploring some fascinating techniques to achieve this, like using photonic crystals.
Photonic crystals. Okay, I'm definitely going to need you to explain that one.
Imagine them as microscopic mirrors arranged in a very specific pattern.
Okay.
They can actually manipulate light bending and focusing it with incredible precision, ensuring that those gasbo cells are capturing every bit of energy possible.
Wow, that's some next-level science right there. It sounds like HLEC has enormous potential, but it's still in its early stages of development.
That's right. It's a rapidly evolving field with a lot of ongoing research, but the possibilities are incredibly exciting, especially when you consider the implications for small modular reactors and clean energy access for communities around the world.
It's mind-blowing to think that we could one day have these tiny, super efficient nuclear reactors powered by invisible light. Okay, so that's HLEC. What about TPV? How does that system work?
TPV, or thermophotovoltaic conversion, also involves converting heat to electricity without turbines, but it takes a slightly different approach instead of focusing solely on direct conversion. TPV systems are all about maximizing efficiency by managing and recycling thermal radiation.
Okay, so how does that work?
We have to remember that not all the heat emitted by the reactor core can be immediately converted into electricity. TPV systems use special filters and reflectors to capture that unused radiation and redirect it back to the emitter. It's like a closed loop that constantly recycles energy to squeeze every bit of power out of the system.
So it's like a super efficient thermal engine constantly reusing energy that would otherwise be wasted. That's pretty clever.
It is, and just like with HLEC, material science plays a crucial role in TPV. One of the key materials here is tungsten.
Tungsten, isn't that what they use in light bulbs?
Yes. It might seem surprising, but tungsten is incredibly resilient to heat.
Huh.
It can withstand the extreme temperatures inside a reactor core without breaking down.
Really?
Plus, it's a great emitter of thermal radiation, which makes it perfect for this application.
Wow. It's fascinating how a material we've known for so long can be reimagined for such cutting-edge technology. It's like giving an old dog a new trick.
Exactly. And it highlights the importance of constantly pushing the boundaries of material science. We're always discovering new properties and applications for existing materials. And that's driving a lot of the innovation we're seeing in fields like nuclear energy.
So tungsten is the workhorse for TPV. Are there other materials involved as well?
Absolutely. Rare earth oxides, for example, play a crucial role in fine-tuning the emitted light spectrum, ensuring it's perfectly matched to the photovoltaic cells for maximum efficiency. But those come with their own challenges, mainly cost and availability.
It sounds like TPV has a lot of potential, but it faces similar hurdles to HLEC in terms of finding the right materials and balancing performance with cost.
That's right. But the research we've seen suggests that both technologies are making significant progress, and there's a real sense of optimism within the scientific community about their potential to revolutionize nuclear power.
Well, I have to admit I'm getting pretty excited about this too. It's amazing to see how scientists are pushing the boundaries of what's possible with nuclear energy.
It is, and what's even more intriguing is that there are companies already working on integrating these technologies into real-world nuclear reactors.
Really? Like who?
One example is a company called LEVPOWER, founded by Dr. Lev Neymotin.
Okay.
They're developing something called the Nuclear Electric Generator, or NEG, which is designed to utilize either HLEC or TPV.
So they're hedging their bets, waiting to see which technology emerges as the front runner.
Exactly. They're essentially building a system that's adaptable and future-proof, ready to embrace whichever technology proves to be the most efficient and scalable. It's a smart strategy that highlights the dynamism of this field.
So for those of you listening, the takeaway here is that there's a real push to make next-generation nuclear power a reality. And it's not just theoretical research. There are brilliant minds and companies actively working to make it happen.
That's right. It's a testament to the power of scientific ingenuity and collaboration. And the results could be transformative, not just for the energy sector, but for the planet as a whole.
Okay, so we've got a good grasp of HLEC and TPV now, but it's almost like they're in a friendly competition with each other.
Yeah.
So in our next segment, let's dive into a head-to-head comparison.
Okay.
Which technology has the edge? Yeah. What are their strengths and weaknesses? And ultimately, which one do WE think has the best chance of shaping the future of nuclear energy? Stay tuned for part 2 of our deep dive.
You know, it's fascinating how both HLEC and TPV are pushing the boundaries of what we thought was possible with nuclear energy.
Yeah.
We often think of nuclear power as this brute force.
Right.
But these technologies are revealing a much more nuanced and almost elegant side to it.
I know. Harnessing the glow of a reactor core to generate clean electricity.
Yeah.
It still blows my mind, honestly.
It's pretty amazing.
And speaking of elegance, we can't forget about the materials involved. They're absolutely critical to making all this work.
That's a great point. Material science is truly at the heart of both HLEC and TPV. It's not enough to just design a clever system. You need the right materials that can withstand extreme temperatures, resist radiation, and function flawlessly for years on end.
Yeah, we've already talked about tungsten being a bit of a superhero in TPV systems,
right?
Handling those incredibly high temperatures like a champ. But what about HLEC? What materials are key players in that technology?
Well, as we mentioned earlier, gallium antimonide, or GasYab, is the star of the show for HLEC. Right. These specialized photovoltaic cells are incredibly efficient at converting that near-infrared light into electricity.
Yeah.
But as with any high-performance material, there are trade-offs.
Right. We talked about the cost and availability of gas being a potential hurdle. So are scientists looking for alternatives, or are they focused on improving GasYab itself?
It's a bit of both, actually.
Yeah.
Researchers are exploring ways to make gas production more efficient and cost-effective, which would be a huge win for HLEC. But they're also looking into other materials that might offer similar performance at a lower price point. It's like a two-pronged approach to solving the problem.
So it sounds like finding the right materials is a bit of a balancing act between performance cost and availability. There's no magic bullet, it seems.
Exactly. It's a constant process of experimentation and refinement. And it's not just about the emitter and the photovoltaic cells. There are all these other components and layers that go into these systems to make sure the energy flow is optimized.
Oh, right. We skimmed over things like photonic crystals and dielectric mirrors. Can you remind me what those do again? They sounded pretty important.
Absolutely. Think of them as highly specialized traffic cops for light.
Okay.
Dielectric mirrors, for example, act like one-way streets, allowing certain wavelengths of light to pass through while reflecting others. This ensures that only the most useful light reaches the photovoltaic cells, maximizing efficiency.
Ah, that makes sense. And what about photonic crystals? We talked about them being like tiny mirrors that can manipulate light.
Right, they're incredibly intricate structures, almost like microscopic works of art, that can bend and focus light with incredible precision. They can essentially channel that light energy exactly where it needs to go, ensuring that the photovoltaic cells are capturing as much of it as possible.
It's amazing how much of this comes down to manipulating light at such a tiny scale. It's like nanotechnology meets nuclear power.
It is, and all of this is backed by sophisticated computer modeling.
Mm-hmm.
Scientists are using powerful simulations to design and optimize every aspect of these systems, down to the arrangement of atoms in those photonic crystals.
Wow, that's incredible. So we've got the materials, the intricate components, the computer simulations, but how do these technologies actually get implemented in a real-world nuclear reactor? Are we talking about massive overhauls of existing plants, or is it something completely different?
That's where the concept of system design comes into play. And the good news is that both HLEC and TPV are incredibly versatile and can be adapted to various reactor types and sizes.
So what are some of the approaches being explored?
For smaller, more compact reactors, something called direct thermal coupling is often used. This basically means that the emitters, the parts that generate light, are placed as close as possible to the reactor core to capture the maximum amount of heat.
Makes sense. Keep things compact and efficient. But what about larger reactors? Can HLEC and TPV be integrated into those as well?
Absolutely. In fact, that's one of the most exciting aspects of this technology. We've seen research on integrating distributed emitter systems into larger reactors. Imagine multiple emitter modules strategically placed throughout the reactor, all feeding energy to a central system.
So instead of relying on one giant turbine, you'd have this network of smaller, more modular units working together. That sounds much more efficient and resilient, right?
Exactly. And that modularity opens up a whole range of possibilities. You could have hybrid systems that combine TPV with other energy technologies like thermoelectrics for even greater efficiency and redundancy. It's a really flexible and adaptable approach.
So it sounds like HLEC and TPV aren't just limited to replacing turbines. They could fundamentally change how we design and operate nuclear reactors in the future. It's like a complete paradigm shift.
It is, but of course, no technology is without its challenges.
Right. We can't get too carried away with the excitement. What are some of the hurdles that researchers are still working to overcome?
Well, material degradation is a big one. Operating in the extreme environment of a nuclear reactor core takes a toll on even the toughest materials. Radiation heat stress. All of these factors contribute to wear and tear over time.
So even tungsten, our superhero material, isn't immune to the ravages of a reactor core.
Unfortunately, no. But scientists are developing innovative solutions like ceramic coatings and radiation-hardened materials to extend the lifespan of these systems and make them more robust.
It's like an ongoing arms race between pushing the limits of material performance and the harsh realities of a reactor environment.
Yeah, that's a great way to put it. Another challenge is thermal management. Keeping those temperatures stable and within the optimal range is crucial for both efficiency and safety. Overheating can lead to reduced performance component failure and even potential safety risks.
So it's not just about generating heat, it's about controlling it with incredible precision.
Precisely. And then there's always the issue of cost, especially with emerging technologies. The initial development and deployment costs for HLEC and TPV are still relatively high.
We talked about the cost of materials being a factor, especially those rare earth oxides used in TPV. But is there any hope that those costs will come down over time?
There is. Research into alternative materials and manufacturing techniques is a top priority if we can find ways to reduce our reliance on those expensive elements and streamline production processes. The cost of these technologies will become much more competitive.
It's kind of like the early days of solar panels, right? They used to be incredibly expensive. But as technology advanced and production ramped up, the price plummeted, making solar energy accessible to a much wider range of people.
That's a great analogy, and we're already seeing signs of that happening with HLEC and TPV. As research progresses and economies of scale come into play, we can expect those costs to come down significantly.
So there are still challenges to be addressed, but the potential benefits of these technologies are enormous. Imagine a world powered by clean, compact nuclear reactors that are safe, efficient, and accessible to communities worldwide. It's a pretty inspiring vision of the future.
It is. And while there's still work to be done, the progress we've seen in recent years gives us a lot of reason for optimism. The ingenuity and determination of the scientific community, combined with the growing urgency of the global energy crisis, are driving a wave of innovation in this field.
It's truly an exciting time to be following these developments. We've covered a lot of ground, from the science of materials to the system designs and challenges, but there's one crucial aspect we haven't addressed yet: the economics. Can HLEC and TPV really compete with traditional energy sources? What are the costs and benefits? We'll delve into those questions and more in the final part of our deep dive, so stay tuned.
All right, so we've gone deep into the science, the materials, the reactor designs, but now let's talk about the bottom line. Can HLEC and TPV actually compete in the real world? Are they economically viable?
Well, that's the big question, isn't it? And it's complicated. We have to weigh those upfront costs against the long-term benefits. Think about the environmental impact and compare all that to what we already have with energy sources. Yeah, and from what we've seen, it seems like that initial price tag for both HLEC and TPV is pretty steep, right? We're talking millions of dollars per megawatt of electricity.
Yeah.
Which is way higher than traditional nuclear, let alone fossil fuels.
True. A lot of that cost comes from the materials we've talked about, like those rare earth oxides in TPV. Incredible performance, but they come at a price.
Yeah, and don't forget about GasAb. For HLEC, it's efficient, but expensive and hard to find.
Exactly. So upfront costs are definitely a hurdle.
Right.
But the thing is, we can't just look at the initial investment.
Oh, so you're talking about like the operational costs?
Exactly. Less maintenance, longer lifespan, things like that.
Okay, yeah.
Both HLEC and TPV are designed to be simple and durable. Fewer moving parts means less wear and tear, which means lower maintenance costs and less downtime.
Right.
And as material science keeps advancing, we can expect them to last even longer.
So it's like the initial price might be high, but over time it could actually be cheaper than traditional nuclear plants.
Right.
With all their giant turbines and complex systems.
Exactly. And then, of course, there's the environmental benefits.
Oh, yeah, absolutely. Can't forget those.
Nuclear power, especially with these new technologies, offers a cleaner, more sustainable future.
Less reliance on fossil fuels, big reduction in carbon emissions, maybe even decentralized power in remote areas. That's huge for the environment.
Absolutely. And those benefits have real economic value, too. As the world deals with climate change and the costs of pollution and environmental damage, the case for clean energy like this gets even stronger.
So it's like we said, short-term costs versus long-term gains.
Yeah.
You invest more up front, but the payoff economically and environmentally could be massive.
Exactly. And there's another factor that could really help HLEC and TPV economies of scale.
Right. Like the more you make something, the cheaper it gets. So as these technologies get better and production increases, we can expect those costs to come down, making them even more competitive.
Precisely like what happened with solar power. Remember, it used to be incredibly expensive, but as technology got better and production increased, the price dropped dramatically, and it's now a viable option for tons of people.
It's amazing to think we could see the same thing with HLEC and TPV. What seemed impossible a few years ago could be reality soon and change the whole energy landscape.
It really is an exciting possibility. Imagine clean, compact nuclear reactors, maybe even small enough to fit in a shipping container, providing reliable carbon-free energy to communities everywhere.
It's a powerful vision, and it seems within reach. We've seen the science, the possibilities, and we've even looked at the numbers.
We have.
Now it's up to us to make it happen.
I think that's a perfect way to wrap this up.
Yeah, this deep dive has been fascinating.
It has, and I hope everyone listening is feeling a sense of wonder and optimism about the future of energy.
We've learned about these incredible technologies that can make nuclear power cleaner, safer, more efficient than we ever thought possible.
Right.
And while there are still challenges to figure out, the progress is truly inspiring.
Thanks for joining us on this journey of discovery.
Yeah. Thanks for listening, everyone.
Remember, knowledge is power, and the more we understand about these amazing technologies, the better we can decide what future we want to build.
Maybe one day we'll look back at this conversation and see it as the moment we first saw the dawn of a new era of clean energy. Until next time, keep exploring, keep asking questions, and stay curious.